Saxon Algebra 1, Lesson 61. Welcome, my students, to the second half of the book / the year. We're right here. Notice that the final lesson in this book is 120. That means that we've started the second half. Holla! All right, we're starting it with a gentle lesson as well. This is a lesson about subsets. This is how we organize numbers into families, if you will, or groups that have common characteristics. It, in and of itself, is not a computation-heavy lesson. It's mostly about ideas, and we're going to take a lot of notes, so, prepare for that. But this will become important. This isn't just random knowledge. This is going to become increasingly important as we go further down the road in math. So bear with us. In its simplest sense, sets mean that we can take a group of numbers for whatever reason we might have, and we can say, hey, look, these numbers are a set. This is set A. We can say that 2 is an element of A because look, there's 2. It is an element or member, and we can say that 5 is not an element of A because I don't see any 5s in there, do you? Beautiful. Okay, let's continue on. Now there's a new set. This is set B. And if you thought A was simple, B has got you B. In this one, we can say that B is a subset. I'm going to write down the definitions of these symbols in just a minute. B is a subset of A, but A is not a subset of B, right? Because everything in B fits into A. So B is a subset of, and this one, A, is not a subset of. And this one means is an element or is not an element. Okay, obviously, this is this one, and this is that one. Okay, so new little symbols, they make a fair amount of logical sense. Let's try a proper example, 61. Okay, we get 3 sets. Set D is 0, 1, 2. There's a comma in there. These are called finite sets, meaning there's a limit to them. There's just a limited number of members or elements to the set. Notice that we define them always with parentheses. I like sets that are listed in order, but they don't have to be. That's not a rule. You can mix up the numbers if you want. What you don't do, what we would never do is repeat. Like we wouldn't have 0, 1, 2, 1, 0, 1, right? You just list each element of the set once. Okay, here comes another set that looks slightly different. Oh, look, I made an E with 4 things. When my daughter, whose name is Emma, my second born, when she was learning to write her name, she thought these were flags and she thought they were really cool. So she would make like 6. She'd write an E like that because she thought that looked way cooler. Okay, ready? 1, 2, 3, ... What does that mean? That means this is an infinite set. It goes on infinitely and it repeats whatever pattern you can discern in the beginning, and we can see, oh, look, it starts with 1 and then it adds 1. So 4, 5, 6, 7, blah, 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 right? G is another finite set that has some slightly different numbers. So now we've got some statements and we're going to say it if they're true or false. E is a subset of G. Well, that's not true. Not only do the numbers not match, but E is infinite and G is finite. So there's no way. That's false. And we say all elements, remember elements is just another way of saying members or items. all elements of E are not elements of G. So, no. Now let's try another one. G is a subset of E. Does it work the other way? Let's see. G is 1, 2, and 5. E is 1, 2, 3, and then so on. So yeah, all of these guys can find themselves in E. So this is true. And we can say all elements or members or items of G are in E. Hallelujah. And one more. D is a subset of E. Now, E is the infinite one, and D is finite. So we look at it and we go, okay, the ones match up, the twos match up. This looks pretty good, except E has no 0. So this has to be false. So close, and yet so far. E has no 0. Do you know that if there's a slashy through there, that's to distinguish the numeral 0 from the letter O. Scientists use it fairly often. Mathematicians use it sometimes. But it's to clarify that this means 0 as opposed to the letter O, if there's any risk of confusion. Okay, so we learned a few new symbols that are pretty logical. We learned a format. We learned that there are finite sets and there are infinite, infinite. The ... is what makes it go on forever. This is all pretty straightforward. Now what we're going to do is we're going to take this information and we're going to use it to talk about bigger sets of numbers. Not just little clumps, but we're going to use it to talk about bigger sets of numbers. So what I want you to do is I want you to draw on your page. I want it big, okay? About 2/3 of the length of your page. We're gonna fill this in with a lot of complicated information, so I want you to have space to do that. Don't make a little scrunchy box. All right, there it is. Put a line across the top and leave that as it is. All right, we're gonna go travel back through time to when you were a tiny baby. And me, I'm sure my mother did this to me too. And we're gonna draw a little box down here and talk about what happened way back at the beginning of our math educations. Probably the first time you were exposed to numbers is when you were a tiny baby. And I guarantee you that it happened after you had a bath, after your mom or dad gave you a bath. They would pull you out of the water, they'd wrap you up in a towel, and they'd be drying you off, and they would count your toes. And then very quickly, you learned to count your own toes. And the way that one was 1, 2, 3, 4, 5, right? 5 little piggies. And it goes on from there, but that's how you learn to count. This set of numbers is called the natural or the counting numbers. Didn't all fit in my box, sorry. It's the natural way we learned how to count. That's how I remember the name of it. And it started with 1, 2, 3, 4, 5. Oh, that was fun, right? Well, you got a little older, you got a little taller, and you learned about a thing called cookies, and you learned about a thing called a cookie jar. I bet you had some kind of cookie jar, or at least a bowl or a plate that cookies were on. And at some point, your little hand reached up to that cookie plate or into that cookie jar or into the box of Oreos, whatever, and you felt around like this, right? I can remember doing that in the cookie jar when I was a little kid. There was nothing there. Oh, you were out of cookies. And a new mathematical concept tipped into your brain. And that is the concept of 0, okay? And we call this group of numbers the whole numbers. Now, I can't entirely explain why the name is what it is, but The whole numbers are just what you learned to count plus 0. That's what's new about the set of whole numbers, is that they include 0. Now you can see the natural counting numbers are a part of the whole numbers, right? Because it just starts with 0 and then it goes on and it includes all of these. That's why we can say the natural or counting numbers are a subset of the whole numbers. It's because they, fit inside, if you will. You know those nesting cups that little kids play with? My kids always played with them in the bathtub. And we had like 12 of them, and they all fit inside each other perfectly. That's what I think of these subsets that we're writing about, are just like that, where they fit inside of each other. Each one is a set of the one that comes after. All right, after you learned about whole numbers, you got a little older and you got a little wiser, and you learned that, you probably learned about in regards to money. You can have money, but sometimes you owe people money. Not only do you not have any money, but you owe your dad $5 for, I don't know, what did you borrow $5 from your dad from? To go to a movie, except $5 wouldn't get you into many movies. Anyway, you borrowed $5 off your dad. Now you owe him money, and that introduces you to the concept of negative numbers, because that's usually the first place we learn, is that not only do you have no money, but you owe your dad $5. That means you have negative $5. And so we learn about a new concept in numbers, and we call them integers. Integers are not only the whole numbers, but the negative versions of those numbers as well. Of course, 0 doesn't have an opposite. 0 is just 0. But it's all of the whole numbers plus their negative partners. And it's, again, these are all infinite sets. I didn't say that out loud. All right, so you learned that it's possible to owe money and that you actually had negative $5. Of course, you've learned more about integers since then, but that's probably the first time you learned about them. Then things got crazy. If you have siblings, you probably learned about this next concept at home, but if not, you learned it in middle school. The next subset are called rational numbers. What the heck are rational numbers? Any number that can be written as a fraction. Well, that includes a lot. That includes, and I'm going to have to write out here because I ran out of space. It includes fractions, duh. It includes whole numbers, because whole numbers can easily be written as fractions, right? So any integer can be turned into a fraction by putting it over 1. Okay, so that includes these. It includes decimals, because we know decimals we can convert. And it includes percents. But it also includes, when we talk about decimals, it includes any infinite repeating decimals that are infinite as long as they repeat. We're going to talk about infinite decimals that don't repeat in just a minute. But infinite repeating decimals are a part of the Rational Numbers Club. There's a lesson toward the end of Algebra 2 where we learn how to take infinite repeating decimals and write them as fractions. It can be done. So any number that can be written as a fraction is in here. And the reason you learned how to do about it is if you have siblings, is that we get really good at creating fractions out with denominators based on how many siblings we have. I come from a family of 4. I was really good at dividing by 4, right? If there were 17 cookies left in the cookie jar. I'm talking about cookies a lot today. I don't know why that is. But you know what I mean? You immediately learn how to divide by the number of siblings that you have, and you're really good at it. I always felt sorry for kids who had 3 in their family because dividing things evenly by 3 is a lot harder. 2 and 4 are pretty easy. And then if you've got more than that, well, you're on your own. You just have to give a piece of it to your mom, right? Like if there's 5 kids in the family, you divide it by 6 and give 1 to mom. Okay, so this side, all of these numbers fit into each other, right? This is like a set of those stacking cups. However, on this side, we have a different group of numbers that do not fit into those cups. These are called irrational numbers. Oh, get it? Rational and irrational, right? Irrational numbers have infinite, non-repeating decimals. And because of that, we can't turn them into fractions, okay? That is the problem. Infinite, non-repeating decimals. For example, one of the classics of irrational numbers that most every student of your sophistication understands is the number pi. It's 3.14 blah, 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 right? It goes on for a long, long, long time, but it doesn't repeat. It's not a pattern. And so that means pi is an irrational number. Another classic example is the square root of 2. There is a number multiplied by itself that equals 2, but it's got a long, infinite tail of decimal points. So these are irrational numbers. They are a separate set. These are the stackable sets that all fit inside each other. This is another guy, but these two together make up what we call the real numbers. Now, I've taught this class for many years. I taught it for the first time in 2001, that like school year. You guys probably weren't even born at that point. No, you weren't. But whenever I teach this in person, there's always someone who asks, oh, like these are the real numbers. So what? There's like the unreal numbers? Yes, as a matter of fact, they are. We're going to learn about them later next year in Algebra 2. But there is another set of numbers that are unreal. We call them, here I have to tip a little bit, we call them imaginary numbers. And I won't go into the details about how or where they come about and how we deal with them. But we can deal with them quite nicely. And then when we put the imaginary numbers and the real numbers together, there's a name for that set as well. Ignore my notes, pretend they're not there. The two together are called the set of complex numbers. And we'll talk about that in Algebra 2 as well as advanced mathematics. All right, so we're not going to go into any depth with these two right now. We're just staying here in this box of real numbers. But I want you to know there's more to it, and we'll talk about that later. For now, we just want you to know that natural fits into whole, fits into integers, fits into rationals, and irrationals are a separate cup of tea. All right, a couple quick problems. 61.2. We are asked 1/2 equals what subset of the real numbers? So we're supposed to pick out which group 1/2 belongs to. Is 1/2 a natural or counting number? No, you don't have a half toe. Well, I mean, maybe, but I don't think any of us were born with half toes. So it's not a half. It's not a whole number. It's not an integer. It's a rational number because it can be written as a fraction, obviously, since it is. So we write 1/2 is an element of the rational numbers. Whoops. Or we can write it as is an element of. That's the better way to write it. I shouldn't write equals. 1/2 is an element of the rational numbers. Oh, okay. 61.3 asks us about 5. Which sets is 5 an element of? Okay, so we always go to the smallest one and start there. Oh, okay, so it's part of the naturals. It's part of the wholes. It's part of the integers. It's part of the rationals. And it's also part of the reals if you want to throw that one in. You could do the same for this one. 1/2 is an element of the reals. I'm going to add that to this one because you want to write as many of the larger categories as it fits into. So 5 is a great example. It's in this one, this one, this one, this one, and this one. 1/2 is only this one and this one. All right, and one more. 61.4 is 3 times the square root of 2. Aha! We know this guy. He's trouble. He's right there. He is an element of the irrationals and the reals. All right, we want to include every group, right? So he's this and this. Let me just make these lines a little bit bolder to remind you that this was extra information. You don't need to worry about that just yet. All right, the last type of example John asks about, let me just show you it because it's easier to do by just looking at the book. Tell whether the following statements are true or false and then explain why. Reals are a subset of the integers. Okay, so let's look at our chart. Reals are a subset of the integers. No, reals are bigger than integers. So the first one is false. I'm not going to write this down. You can see it. It's easy. It's in your book if you ever want to look at this, if you get confused. But just looking at this. Irrationals are a subset of the rationals. No, they do not overlap or fit inside of each other at all. That's false. Irrationals are a subset of the reals. Yes, the reals are the whole thing. So irrationals are real numbers. So that one is true. I'm going slightly out of order, so if you look at these, don't be confused. The fourth one, wholes are a subset of the naturals. No, wholes are bigger than naturals. We could say that naturals are a subset of the wholes, but wholes are not a subset of the naturals. So that one is false. And then the last one, integers are a subset of the reals. Yes, that's true. Okay? So by looking at this chart, you can answer those questions, I think, fairly intuitively. All right, like I said, we're not going to do any calculations with this immediately, but you'll see these ideas creeping more and more often into our problems, and we'll get to the point where we have to deal very directly with this knowledge. So tuck it in your brain, enjoy a relatively low calculation lesson, and I'll see you for 61. Goodbye.